Hello, welcome to my video series of algorithms. This is the second video of Module 4, Greedy Algorithms. In this video, we will discuss the shortest path problem and Dijkstra's algorithm. To motivate the problem, imagine that we would like to travel from Los Angeles to Orlando. Here is a map of some US cities. We can model the map as a graph data structure. In the graph, the nodes represent the cities, and the edges between them are weighted by the toll fees needed to travel between the cities. Our goal is to plan the cheapest route from the starting city to the destination. More formally, we define this problem as the shortest path problem. The input of the problem includes a graph, similar to the US map we have. We only allow non-negative edge weights, since we likely don't have any negative toll fees. In some settings, negative edges do exist, but we will discuss those in later modules. The input graph can either be directed or undirected, and it does not affect the solution we will present here. The input graph includes two special nodes: the starting point, also known as the source, and the destination, also known as the sink. The output is the shortest path from the source to the sink, where by shortest it means that the path has the smallest sum of edge weights. For example, say we begin with LA and wish to go to Orlando. The shortest path on our map is highlighted in red, from LA to Phoenix, Phoenix to Kansas City, and Kansas City to Orlando. The total amount of toll fee for the trip is $35. No cheaper route exists from LA to Orlando. Let's consider some possible solutions to the problem. A naive solution is to enumerate all possible paths between the source and the sink, compute their total weights, and find the shortest path. However, this approach is inefficient. For example, we can construct 6 paths from the graph shown here, such as SAX, SAY, and so on. At each branching node, we can extend the path by choosing any of the outgoing edges. For example, at node S, we could extend the path with the SA edge or the SB edge. Similarly, at node A, we could extend the path with the AX, AY, or AZ edge. Therefore, at each node, the number of different ways we can extend the current path equals the number of outgoing edges the node has. The number of outgoing edges is also called the out degree of the node, and is denoted as D. In other words, for every edge we include in the path, we will need to try D possibilities. If the path includes 2 edges, there will be D squared possibilities. And if the path contains n edges, there will be D to the power of n possibilities. In the worst case scenario, the path may contain all edges in the graph, or E edges. In this case, this approach will have a time complexity of O d to the power of E, which is invisible for large graphs. The second approach is breadth first search, or BFS. BFS is a graph traversal algorithm that visits nodes closer to the source first. In the first pass, it visits all nodes that are adjacent to the source. In the second pass, it visits nodes that are 2 edges away, and so on. You can search online for more information about BFS. When running BFS on our example, in the first pass, it will visit the 3 cities that are adjacent to LA. They are Chicago, Las Vegas, and Phoenix. We mark the visited nodes in green. In the second pass, BFS will visit cities that are 2 edges away from LA, such as Philadelphia, which is 2 edges away from LA via Phoenix. After the second pass, it will visit all nodes. In this case, we can reach the destination Orlando using a path with 2 edges. The path identified by the BFS algorithm is highlighted in red here. It will cost us $36 to go from LA to Orlando. It is not hard to see that BFS can identify the path with the fewest number of edges between the source and the sink. However, even if a path has the fewest number of edges, it may not be the shortest. For example, the BFS path costs $36, but the shortest path that goes from LA to Phoenix, Kansas City, and Orlando only costs $35. Thus, BFS does not guarantee the shortest path unless all edges have the same weight. On the other hand, BFS will be helpful if we want the path that contains the fewest edges. To solve the shortest path problem, we introduce Dijkstra's algorithm. This greedy algorithm minimizes the total cost needed to visit a new node in each pass. It was invented by Dutch computer scientist Dr. Esker Dijkstra in 1959. Let's see how Dijkstra's algorithm works. At first, we begin at the source, LA, and try to construct a path by adding an edge that leads to a new city in each pass. Initially, from LA, we can reach Chicago, Las Vegas, and Phoenix. We color the cities we can reach with a single edge in green. We then calculate the total cost to each city. The total cost should include both the cost we need to reach the current city and the cost to reach the new city. For example, the cost to reach Chicago should be the cost we need to reach the current city, LA, plus the cost we need to go from LA to Chicago. In our example, the cost we need to reach LA is $0, since LA is the starting point. The cost we need to go from LA to Chicago is $15, as indicated by the corresponding edge weight. Therefore, the total cost to Chicago is $0 plus $15, which equals to $15. Similarly, we know the total cost to Las Vegas is $10 and that to Phoenix is $7. The total costs are summarized at the top left corner of the slide. The greedy strategy of Dijkstra's algorithm chooses the lowest total cost. So we visit Phoenix first. Here, we color the corresponding node in the map red to indicate that the city is visited. And we also record the cost required to reach the city. The algorithm considers the shortest path from LA to Phoenix has been determined at the stage. It will never visit Phoenix again with a lower cost. Let's consider the second pass. Visiting Phoenix allows us to reach 3 more cities: Kansas City, Philadelphia, and Orlando. To reach Kansas City, we need a total cost of $15, where $7 was spent to reach Phoenix from LA, and $8 will be spent on reaching Kansas City from Phoenix. Note that the cost of reaching Phoenix is no longer $0 as for LA, and such an existing cost should be included when calculating the total cost. Similarly, we know that we need $42 to reach Philadelphia and $36 to reach Orlando. Now, combining the 2 cities we can reach in the previous pass, we can reach 5 cities in total. Again, we summarize the total cost to those cities at the top left corner. Based on Dijkstra's greedy strategy, we choose the minimum total cost and visit Las Vegas for $10. We also record such a cost. In the third pass, reaching Las Vegas allows us to find new paths to reach Chicago and Kansas City. For example, we discovered the route from LA to Las Vegas and to Chicago, which costs $22. However, the cost is higher than the existing cost of $15, so we discard a new path. Similarly, the route from LA to Las Vegas and Kansas City costs $23, which is also more than the existing cost of $15. Therefore, it is discarded as well. The costs to Chicago and Kansas City are the same, and we can arbitrarily pick one. Say we pick Kansas City and record the total cost accordingly. Next, reaching Kansas City allows us to go to Chicago, New York, Philadelphia, and Orlando. Now, via Kansas City, we can reach Philadelphia with a lower total cost of $38, which is calculated by adding the total cost to Kansas City, $15, and the cost from Kansas City to Philadelphia, $23. We shall update the total cost to Philadelphia to $38. Similarly, we can also find a cheaper route to Orlando via Kansas City, which costs $35 instead of $36. We color the updates in green for the total cost records at the top left corner. We cannot find cheaper routes to Chicago and New York via Kansas City, so we will keep their costs unchanged. Based on the greedy strategy, we choose to reach Chicago and record the cost of $15. Then, via Chicago, we find a cheaper route to New York with a $37 total cost, and we update the best cost to New York accordingly. The new city we can reach with the lowest cost is Orlando, and we can go from LA to Orlando for $35. At this point, we can terminate the algorithm as we have already reached the destination Orlando. We could also proceed to find the shortest path from LA to all other cities. Now, reaching Orlando allows us to discover a new route to New York and one to Philadelphia. But neither is cheaper than the existing ones. Based on the greedy rule, we choose New York and record a total cost of $37. Reaching New York reveals a new path to Philadelphia, but it does not improve the current one. At last, we reach Philadelphia for $38. We have reached all cities and can terminate the algorithm. Okay, let's summarize Dijkstra's algorithm. The algorithm maintains two sets, S and U, where S contains the set of visited nodes and U contains the set of unvisited nodes. Their intersection is an empty set, and their union is the whole set of nodes in the graph. At the beginning, S just contains the source node, and each pass of the algorithm puts one node in U to S. The greedy principle applied here is always choosing the lowest total cost. The intuition is that, since there only exists a fixed number of nodes in the graph, the number of passes needed to visit the whole graph is fixed. Therefore, minimizing the cost for each pass will likely minimize the total cost for the entire run. When calculating the total cost, we add the cost to the current node and the cost of reaching the new node from the current node. Let U be the current node and V be the new node. Also denote DU as the total cost to reach U and LUV as the cost to V from U. Know that LUV is just the weight of the edge UV. The total cost to reach V via U is DU plus LUV. As seen from the example, There could be multiple nodes that have been visited and multiple nodes to visit, which means that multiple nodes may serve as U and multiple nodes may serve as V. Specifically, all nodes in the visited set S that are adjacent to some nodes in the unvisited set U can serve as U, and all nodes in U that are adjacent to some nodes in S can serve as V. This figure exemplifies the case with multiple U's and V's. We have 4 red nodes that can serve as U and 3 green nodes that can serve as V. And there are 6 edges joining a U and a V. So we need to evaluate the 6 edges that can lead to new nodes when finding the minimum total cost. We summarize Dijkstra's algorithm as pseudocode here. You are encouraged to revisit the example introduced earlier to match the steps with the pseudocode. Note that the shortest path problem discussed here contains only one source. Therefore, we call this problem the single source shortest path problem. On the other hand, we also have the multi-source shortest path problem. To solve it, we run the algorithm on each source node. At last, a key observation is that once a node is visited, its shortest path is determined and won't be updated again. It implies that the cost to reach the node must be correctly computed, as the cost won't be updated either. This is a very strong assumption because we make the claim without visiting all nodes. In this case, it is hard to see why those unvisited nodes will not help construct cheaper path. Fortunately, this is guaranteed by the greedy principle of Dijkstra's algorithm, and we will prove this in the next video. In summary, we introduced the shortest path problem in this video. We also presented Dijkstra's algorithm, which solves the shortest path problem when there are no negative edges. In the next video, we will prove the correctness of Dijkstra's algorithm and discuss its implementation details, as well as analyze its time and space complexity. Thank you for watching, and see you next time.